Welcome to Preston New Road, the location of Cuadrilla's shale gas exploration site. It's a unique location in the United Kingdom because for the first time Cuadrilla are going to drill horizontally into the shale rock. Cuadrilla are a Lancashire-based company, experts in searching for the hydrocarbon resources we need to keep our homes warm and our factories operating. Cuadrilla believe that 3.5 kilometres below my feet here are trillions of cubic feet of gas that have been trapped in the rocks for millions of years. On our previous webcast, we toured this site and looked at what was going on the surface. Today, we're going down below to look in detail at what's called the coring operation. Now, last time you were wonderful in sending in all your views and questions, and you can do that again by entering your question in the chat box, details of which are at the bottom of the screen. Our guide today is Hugh Clark, who's the geologist for Cuadrilla on the site. Hugh, if I'd been here hundreds of millions of years ago, would I have been on the land, in the sea, in a desert? What would it have been like?
Well, good afternoon, Jim. Well, you'd have been in all of those, all of the above. So we'd have gone down through mud flats, through tidal lagoons, places like the Sahara Desert, where we see today, places like the Mississippi Delta and the mangroves that we see over in North America, all the way through down to where we get to the Bolan Shale, which would have been a deep, black, dark, anoxic sea, teeming with life and collecting marine material.
Now, I'm going to try and get some sense of the timescale that we're talking about here, because the other day somebody said, oh, well, the Ice Age will have been quite important in the development of this shale gas. The Ice Age, probably sort of only yesterday in the sort of timescale you're talking about? Well,
yes, in geological time, the Ice Age ended around about 10,000 years ago, and that is pretty much yesterday for geologists. When we drill through the Ice Age deposits that we have here, which are very thin, we go straight into a rock in the Triassic period, which is 205 million years ago. And by the time we get to the Bolan Shales, we're back in time by 360 million years, so much longer timescales.
Now, we can't see the Bolan Shales here, but there is, thanks to Mother Nature, a wonderful opportunity to actually see what you're talking about. And in order to do that, we actually went earlier today to the Bolan Fells, where you can actually see what Hugh's talking about on the surface. Up here in the Bolan Fells, we can actually see geology in plain sight. But just before we talk about the rocks, I'm just interested how you got into this field. It was through climbing in hills like this?
Oh, absolutely, yeah. I've been climbing for about 15 years. I love spending time in the outdoors. Spent a lot of time climbing around Stanage Edge and in the Peak District and the Millstone Grit rocks, which climbers love so much. And I've always been a keen scientist, so the combination of being able to look at rocks, apply scientific rigour and method and unpick some of the stories has just been a great passion of mine for quite a few years now. And
I suppose rock climbing, your face is quite close to rock faces, so you can actually see rocks, and so I suppose you get a very close acquaintanceship with it.
Absolutely, yeah. Often, sometimes you're a little too scared to notice what you're climbing past, but you definitely see on a rock face, it can really unpick a story, and you can see a sequence of rocks and the history that goes with those rocks.
Well, a very good cue into exactly what we can see here, and even I, as a complete amateur, can see the layering of this is Millstone Grit here. You can actually see as it's been laid down, I don't know what each band of that would be in terms of years, but you can see the banding there, but also really significantly it actually interfaces with the Bolan Shale. So take us through all this. I mean, first of all, explain why we can see this so clearly up here, whereas at Preston New Road, it's all deep under the ground.
Yes, well, Preston New Road, the site where we're drilling currently, is about 20 miles away from here, so actually not that far away. Yet here we can see the rocks at the surface, whereas Preston New Road we have to drill 2 or 3 kilometres. And the reason we can see them here is because of tectonic forces. So over geological time, these rocks were deposited, laid down the same as the rocks we drill at Preston New Road, under the sea, deep marine environment, but tectonic forces have driven them back up to the surface, and really you can see these rocks all over the Pennine Hills.
And so tell us about this layer and then how it comes into contact with the Bolan Shale.
So this is, as you said, the Millstone Grit, so well known for industrial use all over the north of the UK. Here it's referred to as the Pendle Grit, so Pendle Hill in Lancashire. The thicker bands that you see there, they're the actual grit stones, and what we mean by that is a sandstone that the sand within it is quite coarse, it's quite big, and in between those blocky layers you can see much more almost paper-like layers, and that's the shale layers in between. As we're coming down, we're seeing more and more shale, and we're coming into what you're standing on at the moment, which is the really dark shale, and this is coming into the Bowland Shale. So here we see the Bowland Shale that we're going to drill horizontally into.
Absolutely incredible. So this is the sort of the line between the two.
Absolutely, this is the boundary right here, and this is one of the best localities in the Bowland Fowls to come and explore the Bowland Shale. As we look down the hill here, we see the whole sequence that will take us a kilometre to drill through the Bowland Shale. We can walk 500 metres down this stream bed, and we can unpick the sequence as we go. And
then eventually all this goes. Is sort of subsumed under, what, the Lancashire plain?
Yeah, that's right. So we only have to go almost near where the M6 is at the moment, and the carboniferous rocks, the Bowland shales and the millstone grits we see here, they dip underneath the Fylde, and they go down to a depth of about a kilometre and a half.
Later in this webcast, you're going to show us some of the Bowland shale that you've actually extracted from Preston New Road, but you've got a piece in your hand now, and you were telling me it's slightly different?
Yeah, so I mean, we'll see later, but the colour is very similar. It's dark, and the reason it's dark is because it's got lots of organic matter in, and that organic matter is what actually makes the gas. The big difference here is because it's been at the surface for, well, a few thousand years now, it's much softer, so you can actually pick it apart, and it doesn't seem like a particularly strong shale. It's almost very paper-like. In fact, that's where the word shale comes from. It's from Derbyshire miners saying it's a scaly rock, and over time the word scale got turned into shale. But what you'll see in Preston New Road is the same rock is much more competent.
Would there be gas literally just under the surface here because the Bowland Shale is here?
So these rocks we've tested, and interestingly they haven't been buried as deeply over geological time, so they've produced oil. So if you come here in the summer when the stream bed is a little lower and there hasn't been as much rain, you will find pools of oil within the stream. So it's generated oil, but it hasn't been buried deep enough yet or in the past to start generating natural gas.
Thank you very much for bringing me here on this beautiful autumn day. Well, there's the rig in full operation today, and here's the rig on Hugh's magnificent canvas. Actually, if you look at it there, it looks pretty tiny, but it's even actually tinier than that in reality. And then below it, we see all these layers of rock going right down millions and millions of years ago. So Hugh, please begin our geological history lesson with the Mercia mudstone.
Yes, Jim, so here we start in the Mercia mudstone. This is a rock about 205 million years ago in a geological period called the Triassic. So you might associate Triassic with dinosaurs, and you would be right. So if we were standing right here at this point in time, there could have been dinosaurs walking around. In fact, the environment that these rocks were laid down in were mud flats, and it would have been a very arid climate, very hot, a lot hotter than global temperatures are seen here today. I have a little sample we can look at that was taken from when we were drilling. You can see that it's quite red. It's red because of the iron and the oxygen that was in the environment at the time, and it's quite clay rich. It's not the hardest rock in the world. It's relatively easy to drill through, and it takes us down about 300 meters in depth below where we're standing now.
And then we come to the Sherwood sandstone. I'm not going to suggest that this was laid down at the time of Robin Hood, because it's obviously a heck of a lot earlier than that.
Yep, so we're still in the Triassic period, so still about 205, maybe 210 million years old. Sherwood sandstone, so we've moved into a typical sandstone rock. This is used all over the country for building, makes a great building material. Many churches made out of this rock.
And was this laid down at a time of when it was a desert?
So again, very arid environment. Yes, a desert, something maybe similar to the Sahara that we see today, maybe with a bit more river influence, a bit more water going through it, but again, very, very dry climate at the time. This rock, very important actually to Lancashire and to the UK, because this is the rock from where we produce natural gas in Morecambe Bay and in the East Irish Sea, which has been producing gas to heat our homes for many decades. Here, where we drill it onshore in Lancashire, we don't see any gas in here whatsoever. It's just
Why is
water.
that?
Well, crucially, the gas that we produce from this offshore comes from the same place we're looking, where we're going to go, the Bowland Shale. But here we've got a rock layer in between, which we'll come on to next, called the Manchester Mole, which is stopping that gas going through.
Yes, well, this is a very important layer. Why is it called Manchester Mole?
Well, I presume because you find it in Manchester. I've not actually been there to the outcrop, and marl is a term for again another sort of type of clay rock. You can see it's relatively clay rich, but it also has a bit of sort of a limestone component in it. Now, this would have been laid down in an ancient sea called the Zechstein Sea. And the important thing about that is that particular sea, which was widespread, evaporated over many times. So it would have filled up with water and then evaporated and filled up with water and evaporated. And each time it did, it laid down these layers of rock which are completely impermeable. They don't let gas through them whatsoever. And it's those layers which are keeping a cap on the gas in the Bowland Shale below us.
And crucially, also a cap on any water that would be below it, because there's often talk about, you know, that this whole fracking operation can in some way affect the water supply, which is right up there.
Yes.
This acts as a complete seal for everything between those layers.
So we don't see any hydrogeological, any water connection between what we see above the Manchester Mole or below it, just like we don't see any gas going from the Bowland Shale here up into the Sherwood sandstone. And to put that into context, the areas where you can drill to get water here are all the way back up in the glacial deposits, and we have to go all the way back down to find the gas. So in that way, you can see we're 1.2 kilometres, 1.4 kilometres. That's about 10 Blackpool towers stacked on top of each other to get down to where we are now.
Right. Now we move into the unknown era. Is this because you don't have any facts about it? Well, why don't we know much about this, what's below the Manchester Mole?
So we're jumping here from the Manchester Mole, 250 million years old, and suddenly we have a time gap, a hiatus in time of about 50 million years, and we jump into a different geological time called the Carboniferous, which is about 320 million years old. So there's a big time gap there. And that time gap is what we refer to as the Variscan unconformity. So it's
the Variscan unconformity. It's straight out of Star Trek.
Yes, it's good. So a bit like we see the Himalayas or the Alps today, a mountain building time that we have. This happened, the Variscan mountain building event happened, and while that mountain building was happening, no layers of rock were being laid down. So we had to wait for the mountains to be built, to then be eroded back away before we get all these rocks of the Triassic start to be deposited again.
Next, the Millstone Grit. Now, I know you're a bit of a rock climber, so is this your favourite layer?
Yeah, absolutely. I've spent many hours and days fondly spent on the Millstone Grit. Very coarse sandstone. This one laid down in a deltaic environment. So if you think of somewhere maybe like Bangladesh today, or even the Mississippi Delta, in North America, lots and lots of sand coming off the continent and spilling into the sea, making these big sand lobes, and you can see a very, very coarse sandstone, which is what makes it so grippy for rock climbers. That's why we love it.
And we finally arrive at the Bowland Shale, and this is the really significant thing, because we can see that the arrow, the vertical arrow drilling down, is beginning to go off horizontally here. So this is where the gas is, yes?
Absolutely. So where we're going to try and work out we can get the gas out of. So the Bowland Shale
Oh no, this colour is completely different from what we've seen so far.
Absolutely. So you can see this is a very fine-grained rock. Unlike the millstone grit we looked at, we can't see any sand particles by our eyes. They do exist, but you have to look under a microscope, and it's dark because of the organic content. So the Boland Shale was a shale laid down in a marine, in a sea environment, a deep sea, teeming with organic life, but when that organic life drifted to the bottom of the sea, there was no oxygen there, so it couldn't be scavenged and eaten and taken away. It was preserved within the rock, and that's what gives it the dark colour.
And what strikes me here is that this Boland Shale layer is much thicker than the previous layers we've been looking at.
Absolutely, that's one of the unique things about the Boland Shale here in the UK is its thickness. It's a tremendously thick rock which has this black organic content throughout it, and one of the reasons it's so interesting to us at Cuadrilla Resources is because of the resource size that's available to us. So if we look back up at the one drill pad up there and the drill pad that we stand around on now, you can see that although we show that there's one layer at which we could drill horizontally, we could actually drill horizontally at multiple layers, and that's really important because it means the amount of gas we can extract from the subsurface can be done with just a very small footprint of something the size that we're on today.
Hugh, all I've got to say is thanks to you and your mighty canvas. And Hugh Clark joins me live here on this blustery day, and there's been a lot of questions stimulated, I think, by your canvas diagram, Hugh. The first one comes from Mark, and he's asking about the size of the drill hole. I mean, is it as wide as like a coal mine hole?
No, not at all. So the size of the hole that we're drilling at the moment is 8.5 inches in diameter. So that's probably about the same size as your clipboard that you've got there. That's for the vertical part of the hole that we're doing at the moment, where we'll collect the core. After we finish that whole section, we'll actually drill the horizontal portion of the well, and that will go down in hole size. So that goes down to a 6-inch wide, about this big borehole size. So definitely not. I always think as coal mining, you can go down there, you'd be working in there, there'd be heavy machinery. That's a bit like open hole surgery. This is more akin to sort of keyhole surgery, I'd say. 6 inches, 3 kilometres below the earth is a pretty small.
So the way it was described on your canvas, it's actually much smaller than that. It was larger to scale, just to illustrate where it was going.
Absolutely. If we tried to draw it on scale on the canvas, I think it would have been a very small pen line, or possibly not even visible at all. So it is a very small. If you imagine 6 inches wide, half a foot, very small well bore. Yes.
Okay. Well, thank you, Mark, for that question. Another question now. No name attached to it. It's quite a technical one. How do you determine the direction of maximum and minimum stress in the shale? I mean, is it stressing and flexing down there?
Yes, it is. All rocks undergo stress. I mean, we should probably explain what stress is to start with. That is that the rock under the earth is subjected to different forces, often tectonic forces, but also forces of the weight of the rock above it. So when we talk about stress, we think about them in 3 directions, one being the vertical stress, and that's literally the weight of all the rock above that piece of rock pressing down upon it. And then there's 2 horizontal stresses. Now, normally one of those horizontal stresses will be slightly stronger than the other horizontal stress, and here in Lancashire that's mainly to do with the tectonic strain that we're feeling from actually the alpine building events. So if you went to the Alps and you were skiing in the French Alps today, and the collision of Africa coming into Europe, we're feeling that horizontal stress, not very strong, but we're feeling it all the way up to here in Lancashire. Now, the way that we tell the difference between the minimum and the horizontal stress is by drilling through the rock. As we drill through the rock, we can take an image, so we can go down with a tool that looks at the well bore and takes an image, and generally what happens is you get very small vertical cracks which align with the direction of that maximum horizontal stress.
That's absolutely fascinating. We're actually affected by the collision between Africa and Europe that's obviously spectacularly going on in the Alps, and it also goes to a point that we sort of think that we're in an inactive country here. We don't have those earthquakes, but obviously occasionally there is seismic activity going on. Yeah, okay, well the next question now is, we were talking about the Manchester Marl because you were saying that provided a seal, and so no water can get up into the normal water courses that we drink, for instance. But of course, somebody's obviously pointed out that you have drilled down through the Manchester Marl, so have you broken that seal?
Well, in a way we have. We've drilled through it, so we've made a well bore going through, and a bit like we were talking about the size of the well bores before, the one we're drilling at the moment, the 8.5-inch hole, we were drilling a bigger well bore as we went through the Manchester Mile, so that was about 12-inch hole. So as we went through, we drilled into the Manchester Mile. We would have then put steel casing down into that layer and then cemented that casing to the well bore around it, so it creates a seal where no path or leak can escape. So it's one thing to create that barrier, and it's essentially putting an engineering barrier aligned with a geological barrier, and then we can come in, and once the cement is cured, once it's set, we'll do a hydraulic test. So we'll pressure up the water which is at that barrier and test that there is a hydraulic seal around the wellbore.
The next question that's come in is about your canvas, and I think obviously there's a thought that perhaps it was a bit diagrammatically too neat. I mean, are the layers really as well defined as indicated?
No, diagrammatically it is too neat. It's, it's the best way to try and imagine.
We saw that a bit ourselves
through.
when we went up to the Bowland Fells,
Absolutely.
didn't we? We saw the integration of the shale and the millstone.
Absolutely. The subsurface, the rock around us is more dynamic, more of a dynamic system than we'd believe, and so the rocks aren't always horizontal. Often they're lying at different, what we call dips, so they're dipping beds, 20 degrees, 30 degrees, so they move around a little bit, and then also they have been faulted and fractured over geological time, so it isn't just a sequence of sort of books stacked one on top of each other. Some are slightly slanted and others are slightly kinked because of faults and fractures.
A question here, actually, not about what we've seen so far in this webcast, but a bit of history. Of course, you did do a search in the Preston area of Lancashire. What went wrong there, and how can you avoid that happening again? A question is asking.
Okay, so I'm going to assume that's probably to do with the minor earth tremors that we had in Preston. So that was a well, a bit like this one, a vertical well, where we did some hydraulic fracturing back in 2011. And when that fracturing took place, there were some small earthquakes that happened. Earthquakes that can just about be felt, definitely nowhere near the level that would cause any damage or any structural damage. The difference here is that we've got an advanced earthquake monitoring detective system. So before we actually do any fracturing, and while we're doing hydraulic fracturing, we're going to monitor the earthquakes to a very, very low level to try and put that into if we could think about it in a way that is visible. If we're 2 or 3 kilometers under the earth and we took a can of Coke and dropped it from here to the floor, that's the sort of size of earthquake, a very minor tremor that we'll be able to feel. So by monitoring the real detail of the earthquakes happening, which do happen as you create fractures, we'll make sure that we never get to a point that it escalates or would ever be felt at surface. So it's to do with a mitigation program put in place.
Yeah, it's very important to reassure people about that aspect of it, because it has had a lot of publicity. Now, you showed us, in fact, two samples of shale rock, one which had been weathered, and I think you explained that. But there's a question from one of our people who's watching this webcast today, and do keep your questions coming in, by the way, about the sample that you showed us when we were going along the canvas. And this question relates to it looking very, very dense, very, very thick. The question is, where's the gas in that? Yeah,
well, it's true. There's no obvious place. There's no big void under the ground where all the gas is held. It's held within the rock. Now, that very hard rock, very competent, you can't see it by eye, but there are lots and lots of tiny holes in there, which we refer to as pores. And that rock, believe it or not, is made up of about 4 or 5% airspace. So about 4 or 5% of that total bit of rock we were looking at, although you can't see it, are voids, are pores, and that's where the natural gas is held.
Another question coming in now is about remarks by Professor Underhill. I imagine you know who he is, and he's been doubting whether shale rock is a viable source for gas.
Well, we know through previous work that there's gas in the rock, so we're pretty confident about that, and the geological system that's set up here works as something to produce gas. We know that because we only have to go 10 miles offshore to Morecambe Bay, and we've been producing natural gas there for decades. The big question that we're trying to answer here is whether we can extract that gas at a rate that is going to make a business and an industry here in Lancashire.
I think this is going to have to be our last question in this particular section, and it concerns this Manchester Marl layer, which obviously people are very interested in because of the sort of sealing qualities of it. Does it run right underneath Lancashire and out into the Irish Sea?
It does. It runs all the way out into the Irish Sea. In places in the Irish Sea, it's been faulted, and that's allowed gas to get up and into the Sherwood sandstone, the rock we talked about in Morecambe Bay. And as we go in the other direction to the east towards the Pennines, it peters out and it thins out and comes to a stop once you get to the Bowling Fowls where we were earlier today.
You're a constant fountain of information, but we'll pause that fountain for just a moment because you can keep your questions coming in. Shortly we'll be joined by Nick Mace, who's Quadrilla's Safety and Planning Manager. Questions for him, please. We'll be very, very welcome. But now Hugh and I are going to resume our tour of the site, looking at this whole issue of coring. We're now in the mudlogger's cabin, where we see very much 21st century technology, as opposed to outside where we're dealing with mud and rock. And what are you monitoring here?
Well, actually, Tim, the mudlogger's lab, the primary purpose is safety. So it's monitoring the rig operations, just as the rig monitors its own operations, but independently. So we've got 2 checks of what's happening at the operation at any point in time, monitored 24/7. More interestingly for myself, over here, we talk about some of the equipment which helps inform the geologists. So the first one we have, probably the most basic, is the one called a total gas detector. So as that mud is going around the well bore and the rock's being crushed up, it's liberating some of the gas, and the gas is coming back with the mud. It's being extracted and pulled into this machine here, and it's telling us how much gas is actually within that mud, and therefore how much gas is likely to be within the rock that we've just drilled.
And the other screens sort of break down the analysis a bit more?
That's right, absolutely. So it gets a little bit more complicated. The one above is called a chromatograph, so it's taking the total gas measurement and then it's splitting it down into its different components. So how much methane is there, how much propane, how much butane there is. And the one above that goes just another level of information down, which is those methanes and propanes have carbon within them, and it's actually measuring the type of carbon isotope. So there are different types of carbon isotope, and they can give us indications to things like the gas maturity and also the pressure at which the gas is held within the rock.
Now I see down the far end an old-fashioned instrument, a microscope. We'll come down to that, but more screens as we approach the microscope?
Absolutely. So as you've probably seen previously, a lot of parameters to be monitored. So these are monitoring the rig parameters. So you've got the depth at which we're drilling, how fast the drill bit is spinning around, how much torque and force is on there, how much weight is on top, and then all the levels of gas coming back out the well. So all to do with those safety parameters again.
And here we have the microscope and some of the samples that have come up. That looks like some Boland shale.
That's a bit of Boland shale we have there. Yeah, actually, most of the time they don't look as big as that. It's very fortunate when we get a chip that big. We get quite excited because it gives us something to see. But generally what we're looking at is the drill cuttings that we see here, which are tremendously hard to describe. So the geologist's job is to come over to analyse these through the microscope and do their best job at trying to describe what that rock looks like through a microscope. But you can see here how crushed up and how fine-grained it is. It's really tough job to get the detail out of the cuttings that we'd like to, and that's why we...
And the fine detail is really crucial to this whole operation.
Absolutely.
It's not all the same, you know, samples aren't all the same each day?
Not at all. The devil is absolutely in the detail, the mineral makeup, the thermal maturity. There's all these details that we have to try and extract. We can't do those all by cuttings, by looking through the microscope, but a lot of it is done away in a lab, and a lot of the information that we actually gain is done through the coring operation, where we get physically large pieces of rock that we can look at.
We're now in the core cabin with the canisters with the samples that have come up from deep in the earth. How do you get them up here, Hugh?
Well, Jim, it's a bit like the drilling process. Instead of the drill bit wearing away and creating these little cuttings of rock, it's actually got a hole on the inside, and it will grind away around the rock, and the core sample will fill up inside the actual drill pipe. Now, the thing that we're doing here, which is slightly different and very interesting, is we use what's called a wireline retrieval. So as that core fills up inside the drill pipe at about a 10-metre length, we will go down the inside of the drill pipe with a wire, and we'll pick up that core and retrieve it back to the surface very quickly in about half an hour to get from 2 or 3 kilometres below the earth back up to the surface.
And speed is essential.
Speed is absolutely essential, not just when it gets here, but getting it into this cabin as well. As soon as it gets here, we've got to make sure we can get it into these canisters that we see here as quick as possible, because the whole time that it's coming up the hole and when it's on the surface, it's losing its gas content, and that's the thing that we're trying to measure, so we want to do it as quickly as possible.
And then, of course, you subject it to a number of tests. We've got various machines in this cabin. Can you tell us what one or two of them do?
Yes, I can. So I have a sample here of core, and you can see that it's cylindrical, so it's round. This one's about 2.5 inches in diameter, but you can see that it's flat on the edge here, and that's because after the core sample's been brought up to the surface, we'll take it over to this slabbing machine, and we'll actually cut the core in half, and half of this will be retained by Quadrilla, so we can do further sampling and investigation, and the other half goes to the UK government, actually, the BGS, the British Geological Survey.
And the other machine here?
So this machine that we're seeing here is called a core plugging machine, so we don't have to take the whole rock sample away and take it to a laboratory to understand what's going on. We can just put the sample in here, and we can take a small plug of the sample either in that direction or in this direction to send off to the laboratory.
Okay, well now let's look at this core in some detail, and let's show it to the viewers so that they can see. And I see various marks, so a white mark, and I also see yellow and red. Now, what is the difference in age between those various markings, Hugh?
Absolutely. So I put the yellow and the red on not very long ago, and the reason I put those on there is red for on the right. So when I pick up this sample and I don't forget to put it back down in the wrong direction, so it's upside down. So as long as I have the red on the right, then I know which way up the sample is. The white bit is actually very natural and interesting. So this would have formed probably about 300 million years ago, and it would have formed after the Boland Shale was deposited. And as it was being buried and it started to create oil and then natural gas, it would have started to fracture under the pressure also. And those fractures that happen naturally would have been infilled by fluids, and those fluids create these calcite veins. So calcite's a type of mineral that has infilled the fractures that we see here, the white bits.
And is it those weaknesses that are going to be fracked to get the gas out?
Absolutely. So when you undertake hydraulic fracturing, the hydraulic fracture that's created wants to take the path of least resistance. Here we have lots of paths of least resistance because the rock has already undergone Mother Earth's hydraulic fracture. So when we come along and do the same operation, it will follow the same path, yes.
And in terms of deciding when to fracture horizontally, this sample taking is absolutely crucial in that process. Absolutely
crucial. So the devil in these rocks is really in the detail. So once we send them away and we look at them under microscopes and scanning electron microscopes, very fancy tools, we will also need to know things like the mineral makeup, so the mineralogy. So we're looking at how much quartz is in here, how much limestone, how much clay is in here, and that all relates back to how hard the rock is for fracturing. We're looking at artifacts like how much it's been buried and what was the maximum temperature that it got to, because that tells us the pressure and the amount of gas that might have been able to get into this rock when it was created.
You've given us the geological history earlier in this webcast, but it's not until you actually get the individual samples that you can really go into that sort of detail.
Absolutely. So it's all about getting these samples in here quickly so we can measure the gas, and then out of here quickly into the lab so we can start to understand those finer details that we need to know. Once we've got those fine details, we can start to unpick the whole sequence of the Boland Shale, and we can decide on where the best spots are to drill the horizontal wells.
Now, I know you love your samples so much that you actually are giving them a jacuzzi bath in the next room, so let's go and have a look at that.
Yeah.
Now, Hugh and I have been joking a bit about this being a jacuzzi bath for his samples, but actually, in all seriousness, what's going on here? Warm water?
Yeah, absolutely. So the baths here are full of water, which is supposed to be the same temperature at which these rocks are below the surface of the Earth. Right now. So the temperature here is around 65, 70 degrees Celsius, and that's the temperature at which we'd find these rocks a couple of kilometres below the Earth. So after we've taken this core to the surface, we very quickly typically put it into one of these canisters. We actually purge the canister of the air that's in there with an inert gas, argon in this case, and then we put it into the water bath. Now it will sit in this water bath probably for a number of weeks, and periodically the gentlemen who do the core sampling here will come in and they will put this valve in there and they will measure the amount of gas that is coming out of the rock. So
you're keeping it at the temperature is absolutely crucial to get a true reading.
Yeah, absolutely. And the one thing we can't represent at surface here is the pressure, but we can get the temperature and we can get it up quickly. We can't quite do the same pressure that it would be under the earth.
Well, we've got a video which will show us a little bit more detail what's going on in this tank.
Yeah.
So there we can see for the first time the gas coming off one of the samples. A significant image, that, Hugh.
Yeah, it's just a great video, Jim. I really love watching this video. I mean, we're essentially seeing what's happening under the ground after we've drilled and hydraulic fracturing has taken place. And the reason we can see these bubbles, they're bubbles of methane coming out of the rock, is because we've taken it from deep below the ground with all that pressure, brought it up to the surface and depressurized it, allowing those methane bubbles to escape out of the rock.
But they're escaping very gently at the moment. I mean, how are you going to bring it up to scale in order to produce commercially viable gas?
So exactly what you're seeing is a very small amount of rock. The hydraulic fracturing touches a lot more rock. There's a lot more little fractures going out, so there's a lot more volume or surface area touching that same rock volume, allowing more gas to come to the surface.
Okay, well, as you can see, we're joined by Nick Mace, Quadrilla's Health, Safety, Environment and Planning Manager. Any more titles you want to tell us about?
Certainly keep me busy.
But obviously we've had a lot of rain here in the last few weeks, and there's plenty of puddles around the site. Is this what you expected?
Yeah, so if we go back to 2013, 2014, when we designed the environment statement, what we created there was what we call a bathtub effect. So we deliberately installed a impermeable membrane underneath the stone, and what that does is subsequently allows the site to collect the water to prevent any uncontrolled releases of fluids to the site. So we've accounted for it, it's deliberate, and we've created effectively a bathtub so the environment's protected and there's no uncontrolled discharge to the site. So it's all planned for. If we do get excessive rain, then we have a tankering system in place to take the rainwater away, and we just keep on top of it over and over again.
Okay, well, I think maybe the concern is that there may be sort of some pollutants around here, potential pollutants. What are they, and how are they being managed?
Yeah, again, it all stems back to the environment statement and our permitting process. We had a process whereby we had to do a disclosure of all the chemicals that we're going to use on site, and a lot of also the other chemicals that we use, things like diesel, oils, etc. They're all traditional chemicals you find in the construction industry, your factories, etc. And the processes which you use them are all pretty much well understood. So anything unique that's associated with hydraulic fracturing or drilling, that's all been disclosed, and the control measures that are in place, things like bunding, drip trays, spill kits on site to clean them up, then again that's all been through the process of public consultation, and most importantly as well is regulatory scrutiny.
A more general question now about Quadrilla's role in the Lancashire economy. I mean, you're spending £5 million in the Lancashire economy. Where is that money going?
So primarily it's going into the supply chain, and that's the local supply chain here in Lancashire. So as well as supporting some of the specialist suppliers that we do have, we also need suppliers such as deliveries of logistics, cranes, materials, security personnel. So all that money is going into the local supply chain.
Okay, now we come back to Hugh with the question for you, and a pretty crucial question really. The last question was from Charlie, this one's from Charles. And when do you expect to be feeding gas into the national grid?
Well, we've got a bit of work to do yet, Jim. As you can see, we're drilling at the moment and we're doing the coring operation, and after the coring operation is finished, we've got to work out where we're going to drill the 2 horizontal wells. So that's to do 2 horizontal wells to drill, a kilometre each. Then the drill rig will leave, the fracturing equipment will turn up. We're going to have at least a couple of months of fracturing work to do to get all the fracturing, and then we go into an initial flow test. So that's when we can establish the rate at which the gas is coming out, and then we will know what facilities need to be built and how we can tie it into the national grid. So we've still got quite a few operations to get through before we get there.
Okay, well now we've got a question for you, Nick. You've started to hand money out to local people. Why is that?
I think principally it's sharing in Quadrilla's success. So there's precedent already been set in the renewable energy sector for providing the local community with money from the process that we're doing here. So again, it's really bringing Quadrilla and the community together, and it's effectively, it's, as I said, it's sharing our success.
It's a postcode lottery, though. I mean, who do you decide gets the money?
Well, that goes through a consultation process. The lines are drawn through that process, so it's with the community and with those people who are obviously inside with that postcode, as you say. Then they certainly do benefit, and very much it's within the local vicinity of the site.
Okay, so I'm just listening out for the next question. It's another question for you, Nick. You're doing all your monitoring here, and you're subject to regulation. Are those regulators entirely dependent on what you tell them?
Okay, so in terms of the data that we're collecting, so we have groundwater boreholes, we're doing surface water, air quality monitoring, etc. That all gets submitted to the Environment Agency and also to Lancashire County Council. They're also conducting their own independent monitoring. That's available on something called Citizen Space. So if you Google Citizen Space, you'll be able to see what the Environment Agency's data is picking up. So I know they're doing Carbridge Brook. They've also got an air quality monitoring station at a local receptor. And also there's a number of academic institutions conducting environmental monitoring. So that was all part of the BGS study into proving and providing evidence that this process is safe and reliable. So that data is all available, it's all publicly disclosed. So yeah, it's going to be one of the most monitored sites, if not the most monitored site here in the UK.
Question now for you, Hugh. It's about this the pressure of the rock, pushing the gas out into the wellbore. What sort of pressure levels are we talking about?
So the pressure of inside the rock, which we refer to as the pore pressure, I'm going to use old empirical units now, is in PSI, pounds per square inch.
And we're coming out of the European Union, why not?
That's right. And somewhere in the region, anywhere between around, say, 5,000 to 7,000 pounds per square inch. We actually measure it in a gradient because it's different depths. So often we use PSI per foot to stay in those imperial units.
A question for you, Nick. You're seeking permission for lorry movements at night. Why are you doing this?
So during the summer months, there was quite a large amount of disruption on the Preston New Road, and there was a decision made after a long thought process that went into it to bring the rig on outside of ours to avoid that disruption. Now that disruption is to the local community. It also takes up a lot of police resource and time. So we're applying to the council at the moment to seek only a small number of deliveries that can come outside of normal working hours. Now this doesn't mean that we will use that, it's just an option if we need to, so we're compliant with the planning conditions. And what we've demonstrated in the planning application, so things like noise, the impact associated with those deliveries at night, the evidence collected said that those all compliant with the noise conditions, so it can be done. We're not going to necessarily use it, but it's just an option that we'd like to explore.
We've got another question coming now, going back to the levels of water. I mean, in extreme circumstances, I think the question is asking, if this overflowed here, would your system have failed?
Well, by definition, yes, it would, but we've done a lot of assessment, a lot of design that's gone into this. So the capacity assessment accounts for a 1 in 100 year flood event. This is not a particular site that is subject to flooding. So the whole design and the technique that we've employed here to retain fluid. You can see another tanker as well just leaving, taking rainwater off site. So we've got a program in place that prevents that from even happening. So again, I'm not particularly concerned because of the design and the methodology that's gone into this. It's done specifically to retain the fluid on site, so it's safe.
Okay, I think this is going to be our final question. I'm not sure I entirely heard it because the lorry going past. The drilling. It's about drilling waste. What is happening to all the drilling waste?
Okay, so we've got permitted routes. So again, we've had to go through the Environment Agency process of getting a permit to generate the extractive waste, they call it. That's then split into individual skips when it comes off the drilling mud system. That would be then taken into specific containers, which would be then taken to a permitted waste facility. All that's documented, it's all open to inspection. We have to disclose the data to the Environment Agency. It's all classified, so it's tested, it's monitored, laboratory analysis to make sure that we're classifying and then disposing of the waste streams correctly. So again, it's all in the public domain, it's all been consulted on.
Nick, thank you very much indeed, and particularly to Hugh as well. He's been quite a marathon, and thanks to all of you for so many questions coming in. We are going to keep you updated. We'll be back next month to report on progress. You can check up on our Twitter feed to find out the details of that, and we'll look forward to seeing you again. But for today, from a rather blustery Preston New Road, goodbye.